Imagine gazing up at the night sky and suddenly spotting a dazzling new point of light, so bright it outshines every star and, for a fleeting moment, even rivals the brilliance of the planets. To ancient astronomers, such a spectacle was both wondrous and unsettling, a new star blazing where darkness had ruled. Today we know these extraordinary events as supernovae, the most powerful explosions in the cosmos that humans have ever witnessed. A supernova marks the cataclysmic death throes of a star. When certain stars reach the final stages of their evolution, they can erupt in an explosion so luminous that, for days or even months, the supernova outshines the combined light of billions of stars in its own galaxy. For a brief time, one dying star steals the spotlight from everything around it, releasing energy that can exceed hundreds of millions of times that of our Sun. These events are rare, with only about 2 or 3 expected to light up a galaxy like the Milky Way each century, an approximation within the range astronomers estimate. In fact, astronomers estimate that, on average, one supernova occurs in our own galaxy every 25 to 100 years, though the number is not precise, ranging from 1.6 to 4.6 per century according to different studies. But what exactly happens when a star explodes in a supernova? There are a few ways this cosmic drama can unfold. Sometimes, a massive star, many times heavier than our Sun, exhausts its nuclear fuel. With no more energy to counteract gravity's relentless pull, the star collapses, triggering a violent explosion, a process known as a core collapse supernova. In other cases, a white dwarf, the dense remnant of a once normal star, can be pushed over a critical limit, often by siphoning material from a companion star. When this occurs, runaway nuclear fusion tears the star apart in a thermonuclear supernova. Both scenarios unleash a torrent of light and energy, sending the star's outer layers hurtling into space at incredible speeds. The aftermath of a supernova can be just as striking as the explosion itself. The material expelled often expands to form vast clouds of gas and dust, called supernova remnants, that can span several light years across. These remnants can glow brightly in X-rays for thousands of years, leaving behind ghostly traces that astronomers study long after the initial flash has faded. For most of human history, supernovae appeared as sudden, unexplained lights in the sky. The word nova comes from the Latin for new, reflecting the ancient belief that these were newly born stars. Before the invention of the telescope, observers had no way to distinguish between these rare outbursts and the steadier, more common stars. It was not until the 20th century that astronomers realized the brightest of these new stars were actually something far more dramatic: the explosive deaths of stars, now called supernovae. Historical records show that only 5 such events in our galaxy can be confidently identified as supernovae based on surviving accounts. The earliest known observation comes from 185 AD, when Chinese astronomers recorded a bright star that appeared suddenly in the sky, almost certainly a supernova now catalogued as RCW86. Another event, SN 1006, remains the brightest supernova ever recorded, visible across the world even in daylight. In 1054, astronomers in China and elsewhere saw a brilliant new star that lingered for weeks. Its remnants are now recognized as the Crab Nebula. Later, in 1181, another supernova was observed, and then, during the blossoming of European astronomy, 2 more remarkable events occurred: Tycho's supernova in 1572 and Kepler's supernova in 1604. These last 2 are especially significant, as they were studied with growing scientific rigor. East Asian historical records, particularly those from China, have proven invaluable for reconstructing the history of galactic supernovae. These meticulous accounts provide details on the appearance, location, and duration of these celestial outbursts, allowing modern astronomers to link ancient observations with present-day supernova remnants. Despite advances in technology, humanity has not witnessed a supernova in our own galaxy since Kepler's supernova in 1604. The likely reason is that dust within the Milky Way has obscured any subsequent events from our view. Still, astronomers continue to search for the telltale X-ray and radio signatures of supernova remnants, piecing together the galaxy's explosive history. The study of supernovae took a dramatic leap forward with the invention of the telescope. No longer limited to naked eye sightings, astronomers began to spot supernovae in distant galaxies. This ability has transformed supernovae into powerful tools for cosmic measurement. The explosion of S1993J in the nearby galaxy M81, for example, was identified as a Type 2b supernova, revealing the complex life and death of stars in binary systems. Modern telescopes, such as the Hubble Space Telescope, have allowed astronomers to observe supernovae billions of light-years away, providing crucial information about the size and age of the universe itself. Supernovae are not just cosmic fireworks. Their violent deaths play a fundamental role in shaping the universe. The explosive force of a supernova disperses heavy elements like iron, calcium, and gold into space, seeding the next generation of stars and planets. Without these explosions, the universe would lack many of the materials essential for planets and even life as we know it. Some of the atoms in your body were forged in the heart of a star and flung across the cosmos by a supernova long before Earth itself existed. Despite centuries of observation and research, much about supernovae remains mysterious. Their rarity means that even today, each new event is a precious opportunity for discovery. When a star explodes, it sends a signal across space and time, a message that, for a moment, the universe has changed. In studying these stellar cataclysms, astronomers not only glimpse the death of stars, but also uncover the processes that shape galaxies, build worlds, and, ultimately, make our own existence possible. Every story of a supernova begins in darkness, among the cold, sprawling clouds known as nebulae. Stretching for light years and composed of gas and dust, these nebulae are the raw material of the cosmos, the cradles of every star that has ever shone. Within these enormous clouds, gravity works its patient magic. Over thousands or even millions of years, regions within a nebula slowly collapse, forming dense knots that grow hotter and denser as more material falls inward. These are the earliest whispers of a star's life, the protostar stage, where the future of an entire solar system hangs in the balance. Through this gentle gravitational squeeze, the protostar grows brighter, entering what astronomers call the T-Tauri phase. In this stage, the young star wobbles between bouts of instability and powerful outbursts, shedding material and stirring the surrounding cloud. Eventually, the chaos settles into a steady blaze. The protostar ignites nuclear fusion at its core, forging hydrogen into helium, a sign that the star has entered the main sequence, the longest and most stable period of its existence. Main sequence stars hum with energy, their cores so dense and hot that gravity and pressure hold each other in a delicate balance. For most stars, this is a period of tranquil brilliance that can last billions of years, but a star's fate is written in its mass. The more massive it is, the more violently it lives and the sooner it dies. Small stars burn their fuel slowly, shining for eons before fading quietly. The giants, however, are in a race against time. Stars with more than 8 times the mass of our Sun, for example, roar through their nuclear fuel at a ferocious pace, sometimes lasting only a few million years, a blink in cosmic terms, before their real drama begins. As fusion in the core progresses, a star gradually builds heavier elements from lighter ones. When the hydrogen runs out, the core contracts and heats up, allowing the star to fuse helium, then heavier and heavier elements in turn. The outer layers of the star swell outward. For a star like our Sun, this expansion marks the red giant phase, a gentle swelling compared to what awaits the truly massive stars. Those giants become red supergiants, their envelopes ballooning out to hundreds or even thousands of times the Sun's radius. Their surfaces cool and redden, but inside the core grows ever hotter, forging carbon, oxygen, and elements further up the periodic table. The final act comes swiftly. In massive stars, the fusion process cannot go on forever. Once the core is composed of iron, everything changes. Iron is a dead end for fusion. It does not release energy when fused, so the star can no longer support itself against gravity's relentless pull. At this point, the fate of the star is sealed. The pressure in the core drops, and the core collapses in on itself within seconds, triggering a catastrophic explosion, a supernova. This explosive death is not reserved for just any star. Only those with sufficient mass, typically at least 8 times that of the Sun, will end their lives in such spectacular fashion. The evidence for this comes not just from theory, but from observations as well. Astronomers using the Hubble and Webb space telescopes have identified actual red supergiant stars as progenitors of recent supernovae, capturing the very stars that would soon perish in cosmic fireworks. The aftermath of a supernova depends, again, on mass. For the most massive stars, the collapsed core may become a neutron star, a city-sized sphere of matter so dense that a teaspoon would weigh billions of tons. If the progenitor star is even heavier, the collapse continues, and a black hole is born, an object from which not even light can escape. But the story of supernovae is not limited to solitary giants. Sometimes, the drama unfolds in pairs. In a system like V Sagittae, for example, a white dwarf, the burnt-out remnant of a smaller star, shares a close orbit with a more massive companion. Over time, the white dwarf siphons material from its partner, growing ever heavier. Eventually, the two stars spiral together and merge, unleashing energy in a supernova visible across vast stretches of space. Not all supernovae, then, are the deaths of single massive stars. Some are the result of stellar relationships pushed to their limits. The physical details of a star's demise can vary. While many stars explode while still shrouded in thick blankets of hydrogen, astronomers have also observed supernovae from stars that had already shed their hydrogen envelopes. Such stars may have experienced violent eruptions or steady mass loss in the years before their final collapse, stripping away the outermost layers and leaving behind a core exposed to space. The result is a supernova that unfolds differently from those wrapped in their original hydrogen, offering astronomers clues to the complex path stars can take toward their end. There are even more exotic possibilities, especially when considering the universe's earliest, most massive stars. In the first generations after the Big Bang, some stars may have reached masses of 140 to 260 times that of our Sun. For these titans, theory predicts a unique fate, the pair instability supernova. In this process, the energy at the star's heart becomes so intense that it creates pairs of electrons and their antimatter counterparts, positrons, disrupting the balance and triggering a runaway collapse and explosion. Unlike other supernovae, which leave dense remnants behind, a pair instability supernova can tear the star apart so completely that nothing of the core remains. Evidence for this process has been seen in the chemical fingerprints of a peculiar star in the halo of our galaxy, suggesting that these extraordinary explosions once played a role in shaping the cosmos. With each supernova, the story comes full circle. The heavy elements forged in a star's life and death are flung outward, mingling with the gas and dust of the interstellar medium. These enriched clouds become the seeds for new generations of stars. Stellar evolution is, at its heart, a cycle of birth and death, creation and destruction. The spectacular endings of massive stars, whether as supernovae, neutron stars, or black holes, are not just acts of cosmic violence. They are, quite literally, the engines that drive the evolution of galaxies and the possibility of life itself. In the grand theater of the universe, the life and death of stars is a drama that began billions of years ago and continues, unseen, all around us. To the casual observer, all supernovae might appear to be the same kind of cosmic catastrophe. A distant star suddenly detonates with unimaginable force. Yet, as astronomers have peered deeper into the universe and focused their telescopes on these distant explosions, a more nuanced picture has emerged. These cosmic fireworks are not all cut from the same cloth. Supernovae come in a rich variety, each type shaped by its own underlying mechanism and by the character of the dying star itself. The differences can be subtle, yet they are profound, revealing not just how stars die, but how the universe recycles its material and measures its own vastness. At the heart of supernova classification lies a simple question: what does the star's light reveal? Astronomers have learned to read the light emitted by a supernova using a spectroscope, a tool that splits starlight into its constituent colors. This spectrum acts like a fingerprint, showing which elements are present and, crucially, which are missing. The presence or absence of hydrogen lines in the spectrum is the first clue. If hydrogen is visible, the supernova is called type 2. If hydrogen is absent, it falls into the broader category of type 1. But the story quickly branches from there, with each spectral signature pointing to a different fate and a different origin. One of the most significant discoveries in modern astrophysics is the distinction between two primary mechanisms behind supernovae. Some arise from the deaths of massive stars. These are the core collapse supernovae, representing a spectacular finale to a star's life. Others begin with a quiet, unassuming white dwarf, a stellar ember locked in a gravitational dance with a companion star. In these binary systems, a white dwarf can accrete matter from its partner, growing heavier and denser until it crosses a critical threshold and explodes in a thermonuclear blaze. These are the Type 1a supernovae, and their uniform brightness has made them invaluable tools for astronomers measuring the scale of the cosmos. Let's first explore the core collapse supernovae, the fireworks that result from the demise of stars at least 8 times more massive than our Sun. In the final moments of such a star's life, its core contracts and heats up, pushing the material to incredible densities and temperatures. When the iron heart of the star can no longer support its own weight, collapse happens in a fraction of a second. The result is a shock wave that rips through the star, blowing off its outer layers and leaving behind a dense remnant, a neutron star, or, in the case of the most massive progenitors, a black hole. This rapid implosion and subsequent explosion forge the heavier elements, scattering them across the galaxy. core collapse supernovae are further divided based on what remains in the star's outer layers at the moment of explosion. The classic Type II supernovae are recognized by the strong signatures of hydrogen in their spectra. These events typically occur in regions teeming with young, massive stars where the stellar victims have retained their hydrogen-rich envelopes. Some Type II supernovae, known as Type IIp, display a light curve, a plot of brightness over time that features a long, luminous plateau. This plateau is a result of the hydrogen envelope slowly recombining and emitting energy over weeks or months. Others, known as Type IIl, show a more linear decline in brightness. The distinction between these subtypes comes down to the details of how the star sheds its outer layers and how the explosion unfolds. Not all massive stars die with their hydrogen envelopes intact. Some lose these outer layers through powerful winds or by transferring mass to a companion star before the final collapse. When a stripped-down core explodes, the resulting supernova lacks hydrogen lines and instead may show evidence of helium. These are classified as Type Ib supernovae. If both hydrogen and helium are missing, the event is called Type Ic. The differences are subtle to the eye, but in the spectrum, they stand out. Type Ib and Ic supernovae are a testament to the complex evolution of massive stars and the influence of their environments, especially in binary systems where mass exchange can dramatically alter a star's fate. While core collapse supernovae are diverse, a reflection of the many paths a massive star can take to its end. The Type I, a supernovae, are remarkably uniform. They are the great cosmic yardsticks, so consistent in their peak brightness that astronomers use them as standard candles to measure distances across the universe. The mechanism here is fundamentally different. A white dwarf, composed mostly of carbon and oxygen, is the remnant of a star not quite massive enough to collapse on its own. In a binary system, this white dwarf can pull material from its companion, gradually increasing in mass. When it nears a critical value, about 1.44 times the mass of the Sun, known as the Chandrasekhar limit, the pressure and temperature inside the white dwarf soar. The carbon and oxygen ignite in a runaway thermonuclear reaction, unbinding the star in a fraction of a second and releasing an immense burst of energy. The light from a Type I, a supernova, lacks hydrogen and helium lines. Instead, it features a distinctive absorption line from silicon, a byproduct of the explosion. Because the underlying mechanism is so consistent, Type I supernovae shine with nearly the same intrinsic brightness no matter where or when they occur. This property has allowed astronomers to map the expansion of the universe itself, revealing, for instance, that the universe's growth is accelerating, a discovery that led to the concept of dark energy. Yet the universe is never content with simplicity. Even within the familiar categories, astronomers have uncovered further subtleties. In recent years, new types of supernovae have been discovered through wide-field surveys and telescopes like pan-stars, expanding the classical classification scheme. Some of these rare events challenge traditional boundaries, hinting at exotic mechanisms or unusual progenitor stars. One such class involves extremely massive stars, those with initial masses between about 90 and 130 times that of the Sun. The fate of these giants can be especially dramatic. Under particular conditions, the intense energy in their cores creates pairs of electrons and their antimatter counterparts, positrons. This pair instability robs the core of pressure support, leading to a collapse and, in some cases, a series of titanic explosions. These pair instability supernovae are exceptionally bright and may leave no remnant at all, dispersing every atom of the star into space. Through all these types and mechanisms, supernovae are more than just cosmic spectacles. They are forges, creating most of the elements from carbon up to nickel, and even heavier elements in smaller quantities. The shock waves from their explosions drive the chemical evolution of galaxies, shaping the environments in which new stars and planets form. The classification of supernova, grounded in careful observation of their spectra and light curves, is not merely a matter of celestial bookkeeping. It is a key to understanding the profound processes that govern the birth, life, and death of stars, and by extension, the ongoing story of the cosmos itself. Each type, each mechanism, reveals a different facet of the universe's relentless creativity and destruction, reminding us that every explosion is both an ending and a new beginning. When a supernova tears itself open, the violence is spectacular, but its true legacy lies in what follows. The aftermath of these explosions ripples outward, altering the very structure and fate of galaxies. In the wake of a supernova, vast quantities of energy and matter surge into the surrounding interstellar medium, setting the stage for profound and lasting change. The material ejected, rich with elements forged in the heart of a star and during the explosion itself, does not simply fade into emptiness. Instead, it enriches the cosmic environment, providing the essential ingredients for new generations of stars, planets, and even the building blocks of life. As the shock wave from a supernova plows through space, it sweeps up clouds of gas and dust, sometimes compressing them until gravity takes over and new stars are born. Astronomers have observed that these shock waves can trigger star formation by sweeping over dense molecular clouds, like a cosmic broom stirring up the raw material for stellar nurseries. The effect is not universal. Whether a supernova triggers new stars depends on the conditions of the local environment, but the evidence is clear that, in many cases, these explosions act as catalysts for both birth and destruction. The shells of material thrown off by a supernova do not disperse evenly. Instead, the ejecta can fracture into dense shells, which cool more efficiently than diffuse gas. This cooling is crucial. Only when gas cools can it collapse under its own gravity to form stars. In this way, supernova remnants can directly seed new stellar systems. The interplay between energy, matter, and cooling creates a turbulent environment, one where filaments and structures emerge, shaping the very architecture of galaxies. But these explosions do far more than merely stir up gas. They are the universe's primary factories for heavy elements, those chemical building blocks essential for the creation of planets and, ultimately, for the emergence of life. The iron in your blood, the calcium in your bones, even the gold in a wedding ring, all owe their origins to the cataclysmic dispersal of matter from supernovae. In the violence of the explosion, elements forged over millions of years inside the star are blasted outward, mixing with the galactic medium. As supernovae distribute iron and other heavy elements, they lay the groundwork for the formation of rocky planets and complex chemistry. This process, known as chemical enrichment, is not a one-time event, but an ongoing cycle. Each supernova leaves the galaxy a little richer in elements heavier than hydrogen and helium. Over cosmic time, the repeated contributions from countless supernovae transform the composition of galaxies, inching them closer to the conditions necessary for life as we know it. Without this continuous enrichment, the universe would remain a barren expanse of hydrogen and helium, devoid of planets and the possibility of living things. Supernovae also have a dramatic influence on the overall structure and evolution of galaxies themselves. The energy released in these events is not just a local phenomenon, it can shape galactic gas on grand scales. When a supernova explodes, it transfers tremendous amounts of energy to the surrounding interstellar medium. This energy heats, ionizes, and stirs the gas, sometimes driving it outward in powerful flows. In the early universe, supernovae were so numerous and energetic that they could even cause entire galaxies to lose gas, affecting not just their star formation rates, but also the metal abundances in their cores and halos. Feedback from supernovae, the way their energy and material reshape their environment, has been shown to be one of the dominant forces controlling star formation in galaxies. Modern simulations reveal that supernova explosions regulate how quickly galaxies convert gas into stars. Too many supernovae, and the gas may be blown away or heated so much that new stars cannot form easily. Too few, and unchecked star formation might consume gas too quickly, leaving a galaxy to fade into darkness. On a more intimate scale, supernovae create turbulent pockets in the interstellar medium, mixing and sculpting the gas into filaments and bubbles. These structures are not random. They influence how and where future generations of stars will ignite, and even help define the boundaries of the heliosphere, the protective bubble around stars like our Sun. Ancient supernovae have shaped the very environment in which the Sun and its planets travel, influencing how cosmic rays reach the solar system and, by extension, the conditions on Earth. The blast waves and shock fronts generated by supernovae are not silent. They interact with their surroundings, generating radio waves, X-rays, and sometimes even neutrino signals that can be detected on Earth before the explosion's light arrives. These shock waves provide a unique window into the geometry and dynamics of the explosion itself, revealing asymmetries and instabilities that disrupt and enrich the surrounding medium. Observations of these remnants have shown astronomers not just the violence of the event, but also the complex processes that govern how energy and matter are redistributed in the galaxy. Not every event that looks like a supernova ends in destruction. Some so-called imposters are less luminous eruptions, where the star survives but still ejects material and dust into space. Even these imposters contribute to the ongoing enrichment of the interstellar medium, though their role is smaller than that of true supernovae. Supernovae are also sources of cosmic rays, high-energy particles that permeate the galaxy and can influence the chemistry of planetary atmospheres. As their shockwaves race through space, they transfer kinetic and thermal energy to the surrounding gas, ionizing atoms and generating turbulence. These processes help to maintain the dynamic, ever-changing nature of the interstellar environment. From the earliest epochs of the cosmos, supernovae have played a central role in shaping the universe. Observations have detected their signatures as far back as 730 million years after the Big Bang, showing that even then, these explosions were sculpting galaxies, dispersing heavy elements, and setting the stage for everything that would follow. Today, machine learning tools allow astronomers to classify and study supernovae in unprecedented detail, uncovering new insights into their impact on the cosmos. In the end, the legacy of a supernova is not just written in light, but in the transformed matter and energy it leaves behind. These explosions are the engines that drive the chemical and structural evolution of galaxies, the spark that ignites new stars, and the origin of the elements that make planets and people possible. Every atom heavier than helium owes its existence, in one way or another, to the aftermath of a star's final, spectacular act. Astronomy, at its core, is the art of watching the sky change. For centuries, supernovae announced themselves unexpectedly, sudden stars blazing into existence where none had been seen before, only to fade into memory. Today, however, the study of supernovae has become a race against time, transformed by technology, collaboration, and a new generation of tools that peer deeper into the cosmos and respond faster than ever before. Modern supernova research begins with digital eyes sweeping the heavens. Projects like the Young Supernova Experiment and the Panoramic Survey Telescope and Rapid Response System telescopes scan vast stretches of sky night after night, creating a living record of the universe in motion. These surveys, powered by sensitive detectors and sophisticated algorithms, are always searching for the telltale flicker of a new explosion, a point of light that was not there the night before. Sometimes, these events are so distant that their light has traveled billions of years before finally reaching a sensor on Earth. Other times, the signal is fleeting, a cosmic firework that demands immediate attention. In this field, speed is everything. The earliest moments of a supernova, just hours after the explosion, are rich with information. The first flash of light, the composition of the outer layers, and the signature of whatever mechanism triggered the blast. New methods now combine wide-field sky surveys with rapid telescope follow-up, enabling astronomers to catch these events within hours of their birth. When a supernova is flagged, telescopes around the world can respond almost instantly, capturing its early spectra and providing crucial clues about its origins data that would be lost forever if even a single night passed unnoticed. The sheer volume of data produced by these surveys is staggering. Every night, thousands of new alerts might pour in, most of them simply noise, asteroids, variable stars, or instrumental glitches masquerading as cosmic explosions. Here, artificial intelligence has become an invaluable assistant. At the University of Oxford, astronomers have developed artificial intelligence-powered tools that sift through this torrent of information, filtering out false positives and highlighting the most promising supernova candidates. These systems have dramatically reduced the workload for human astronomers, freeing them to focus on the events that matter most. Tools like SNI Score, a machine learning classifier, now autonomously sort supernovae into categories based on their observed properties, ensuring nothing slips through the cracks. Decision tree algorithms, such as those used by the virtual research assistant, further refine the process, helping astronomers prioritize which candidates deserve precious follow-up time. Yet even before the first visible light reaches Earth, other messengers may arrive. Neutrinos, ghostly particles that rarely interact with matter, can escape a collapsing star's core moments before the explosion becomes visible. Networks of neutrino detectors, such as the Global Supernova Early Warning System, stand ready to pick up this subtle signal. When a burst of neutrinos is detected, SNEWS can send out automated alerts to observatories worldwide. This early warning gives astronomers a valuable head start, allowing them to train their telescopes on the right patch of sky before the visible fireworks begin. Once the explosion is detected, the chase is on. Rapid response telescopes like the Very Large Telescope in Chile have, for the first time, captured the shock wave of a supernova as it bursts through the star's surface, a fleeting moment that reveals the raw power of the blast and the structure of the star itself. In one recent case, the Very Large Telescope was able to observe the explosion's shape just hours after detection, demonstrating the vital importance of quick action. These early observations are crucial, as the initial light carries the fingerprints of the processes that initiated the explosion, clues that fade as the expanding debris cools and the supernova settles into its longer-lived afterglow. The debris from the explosion, known as the supernova remnant, becomes a laboratory in its own right. Astronomers study these remnants across the electromagnetic spectrum, from radio waves to X-rays, probing the composition, temperature, and movement of the expanding material. Each wavelength tells a different part of the story. Radio emissions reveal the interaction of the shock wave with surrounding gas. X-rays expose the hottest, most energetic regions, and optical light shows the spread of newly forged elements. Modern observations have begun to uncover new details about the shape and dynamics of these remnants, challenging earlier assumptions that supernovae are simple, spherical explosions. Instead, evidence now points to complex asymmetries and turbulence in the explosion mechanics, insights only possible thanks to coordinated, multi-wavelength campaigns. The power of modern technology is perhaps best illustrated by discoveries at the edge of the observable universe. NASA's James Webb Space Telescope, with its ability to see in the infrared, has identified the earliest known supernova to date, an explosion that occurred when the universe was less than 1 billion years old. This achievement highlights the capability of Webb and its predecessor, the Hubble Space Telescope, not just to spot distant explosions, but to pinpoint the actual stars that exploded. For the first time, astronomers can link specific progenitor stars to their explosive fates, providing direct evidence about which stars die as supernovae and which quietly fade away. Some of the most tantalizing mysteries in supernova research remain unsolved. Recent discoveries have revealed entirely new classes of explosions, some of which may be powered by quantum electrodynamic cascades. Exotic processes also being studied in connection with phenomena such as fast radio bursts. The connection between supernovae and these brief, intense flashes of radio energy remains an area of active investigation, one that promises to reshape our understanding of both phenomena. Looking ahead, the field is poised for another leap forward. The Vera Rubin Observatory, set to begin a decade-long survey of the sky, is expected to detect supernovae in numbers never before possible. With its enormous camera and rapid cadence, Rubin will transform supernova discovery from a rare event to a nightly occurrence, opening the door to statistical studies that were once unimaginable. Ongoing improvements in artificial intelligence, detector sensitivity, and global coordination will ensure that each new explosion is caught, classified, and studied with unprecedented speed and detail. Yet, for all this progress, supernovae remain stubbornly enigmatic. The precise mechanisms that trigger some types of explosions, the diversity of their shapes and energies, and the role of exotic physics are all questions that drive researchers to keep watching the skies. The story of supernovae is still being written, one flash at a time, one discovery at a time, as astronomers use every tool at their disposal to unravel the secrets of the universe's most spectacular deaths.